In this example, we deal with a more complicated pipe. Okay, it looks more complicated than the previous example, but I will show you that this is actually as easy as that one. So it just has two turns. There's one more turn than the previous one. Will it be only more complicated in terms of finding the correct arms to determine the moments, right? So let's look at this one. For the beam shown here, the external diameter D is given, and thickness is 7.5 millimeter. To determine the stress element, it just determines the normal stress and the shear stress at this point, H. I assume that the A, B, C, 120, 50, and 30 centimeter, okay, the PX, PY, PZ have been given. And the PX, PY, PZ are all in positive X, Y, Z directions. Okay, the three dimensions, A is 120 centimeter, so it will be 1200 millimeter. Okay, the B will be 500 millimeter, and the C will be 300 millimeter. Okay, the PX, PY, PZ are all in Newton directly, so we'll just use the Newton, millimeter, and MPa to do this calculation. Okay, so you would just need to follow the same steps as the previous one. Then first of all, we determine the internal forces based on the external loading. Then we will calculate the section properties, then solve the normal stress and the shear stress step by step. Okay, in step 1, we will analyze the internal forces. This will be internal forces. Then we'll just use the table. Okay, we use the big table. Since here, so if you look at point H and you cut it here, so which is the axial direction in this case? X, right? So X will be the axial direction. So the forces will be Fx, Vy, Vz, right? So correspondingly, you will have if the moment is about x-axis, it will be a torque. Otherwise, about yz directions, it will be bending moment. Okay, so my, mz. And the external loadings, you have px, py, pz. Px, 300 Newton. Py, 1200 Newton, PZ 450 Newton. Then let's look at Fx first. So which one of these three external loading will make Fx? So obviously only one, right? Only Px. That will be 300, 0, 0, right? So how about Vy? And again, there's only one component. You have a 0, 1200, 0. Vz, again, just 0, 0, 450, right? So how about Tx? So which ones of these three external components, external loading, will make torque about x-axis? Will Px make a torque? No, the parallel, right? So Px is parallel to x-axis. So you will have a 0 here. So how about Py? Does Py make a torque about x-axis? Yes, right? So Py, what is arm of Py? A, B, or C? Arm will be B, right? So here, this torque components will be Py times B, or 1200 times 500. How about PZ? Does PZ make a torque about x-axis? Yes. So what is arm? A, B, or C? Arm is C, right? So here is a PZ times C, or 400 PZ times C, or 450 times 300. So what are the signs of these two components? Look at Py times Py times B. Py times B with respect to about the x-axis. Use your right hand rule. Will use your right hand rule with your thumb pointing the positive x direction? Will be the Py B in the same direction as your fingers? Yes, meaning that it's a positive, right? So this is a positive torque. How about PZC? PZ times C. Right hand rule. You can determine that this is a positive torque again. Okay, both of them are positive. Then how about My? So does Px make My? Sure. Right. So what is arm? A, B, or C? It's B, right? So let's draw the cross section here. Okay, draw the cross section at point H here. The cross section is a circle, and your point H is on the top, and your y-axis is here. C-axis is here, right? Then about y-axis, then just if you have Px and the arm will be B, right? Px times B will be one component of My, right? So that will be Px is 300 times 500. How about Py? Py is in parallel with y-axis, so here it's 0, right? Parallel 0. How about Pz? Pz will make a bending moment, My, right? So what is arm? A, B, or C? This will be A, right? So Pz times A. So you can see that the most difficult part of this problem will be finding the correct arm. Okay, to try to understand why I'm using A, B, C as arms for different forces. And target properties, right? This target internal forces, the torque, the M, the bending moment. Why we're selecting different ABCs for different forces to determine them. So here's the Pz times A. This will be 450 times 1200. Okay. So do these two components have the same sign? Okay, so look at Px times B. Px times B will make the bending in this direction. And Pz times A will also make it bending in this direction, right? So these two things will have the same sign, but it's not easy to determine if they are positive or negative. But this is less important. You just need to analyze if they will make a positive or negative stresses, bending stresses at point H. Right? Just keep in mind they have the same sign. Just when you combine them, you can just add them together. Right? They have the same signs. Right? Let's note them here. They will have two components have same size. But this is not important. Since what? Look at this cross section at point H. Well, when you have my, this point H is actually located on the neutral plane, right? The neutral plane. So the y value, the distance from it to the neutral axis will be 0, right? Since y equals 0 in my over I. So when you use this my to calculate the bending stress at point H, that will be just 0. So you just not need to combine them to calculate the detailed values of my at all. You do not need this calculation, right? If you are requested to calculate normal stress at this point, another point here like H prime, right, you will be combine them together. But since this is not requested in this problem, so we will not need to calculate it at all. Okay, so in the end we'll look at mz. Does px make mz? Px, of course it will make mz, right? What is the arm? A, B, or C? It will be C, right? So here it will have a px times C, or 300 times 300. How about py? Sure, py will also make mz, but what is the arm? Py to z-axis. The arm will be A, B, or C. Will be A, right? So here we will have py times A. It will be 1200 times 1200. Then the pz in parallel with z-axis. Okay. So here will be 0. Now let's look at these two. Compare these two bending moments, mz components. Do they have the same sign? Okay, look at px times c. Px times c will tend to bend these components in such a direction, right? So it will make this cantilever part cry. So this will be a negative bending moment, right? This will be negative bending moment. How about py times a? Py times a will tend to bend it upward to make it smile. So this will be a positive bending moment. Okay, so you will have opposite signs of these two components. So you should know what to do when you combine together to determine mz. Right? So we'll do this later. So in the second step, we calculated the section properties, and we have known that the D is 75, and the thickness 7.5. Then the internal diameter can thus be calculated. That will be 60. Right, then C. This is the just the distance from point H to the centroid, right? This C will be half of the external diameter. That will be 75 over 2, 37.5. Okay, knowing these values, we can calculate the cross-section area. Cross-section area will be pi over 4 d squared minus d squared. This will be 60. And Q max is just the maximum possibility of the Q value when you use VQ over IT to calculate shear stress, right? The Q max for a circular shape, the cross section, will be 1 over 12 d cubed minus d cubed. Okay, we have this equation provided in the slides of chapter 7. Okay, go back to check them, to check this equation, and how, more importantly, how to determine the t in VQ over IT, how to determine that t value there. Just to go back to look at that slides. Okay, this result here will be 160. Then we also need to determine the I value, moment of inertia. That will be pi over 64 d to the fourth minus d to the fourth. This will be 917,000. When you use the torque to determine the shear stress, you will need to use that tau equals Tc over J. So the J for a circular shaped cross section will be just 2 times I, right? 2 times I, or pi over 32 d to the fourth minus d to the fourth, right? So this will be 2 times I. It will be 1.834 million. Okay, knowing these numbers, we will be able to calculate the normal and the shear stresses. Okay, in the third step, we will calculate normal stress at point H. Okay, the first component, sigma 1, is due to the axial loading. Right, here we have the Fx over A. Right, the Fx is just 300, and A is 3330. Right, here you will have 300 over 6360. That is 0.047 MPa. And the second component, sigma 2, due to my, right? Due to my, so just my times a y value over I, right? This is 0 as we just analyzed. This is 0 since this y equals 0. Okay, so we do not need to combine these two components of my to get an overall value of my at all. Okay, we can skip this step. Then let's look at the normal stress, sigma 3, due to mz. Okay, that's mz times c over I. Right. Well, the mz here, you have two components. One is negative 300 times 300, another is positive 1200 times 1200. Right, so the mz here is negative 300 times 300 plus 1200 times 1200. Okay, the result is 1.35 million Newton millimeter. Okay, so here the MZ is 1.35 million times C is 37.5 over I is 917,000. You will have 55.207 MPa. Okay, so but is this stress sigma 3 positive or negative? Positive or negative? We just look at these two as we just analyzed. The negative 300 times 300 and the positive 1200 times 1200. The first one will tend to bend it downward, and the second one will tend to turn it upward. So the overall effect will be a positive bending moment. So make this cantilever part smile. So as a result, will this point H be in compression or tension? In compression, right? So here will be a negative value. So here this value is negative. So we can calculate normal stress at point H by just adding these three values together. Right? You will have a 0.047 plus 0, then minus 55.207. Okay, so the result will be negative 55.16 MPa. Okay, so then let's look at the shear stress. Shear stress at point H. So for this, you just also need to realize that you may have three different things to contribute to the overall shear stress at point H. Well, they are the torque, Tx, and these two shear forces, Vy and Vz, correct? So here we need to examine three things. Is the torque, tau x, and Vy, Vz. Okay, you just need to examine these three things. So the first component of the shear stress, tau 1, is induced by the torque. If you use the torque, the equation will be Tx times C over J. Right. So what is the Tx? Tx here equals. Look at here. You have two components, both positive. Right. The first components, second component, both positive. Right. You just add them together. Right. So the Tx here is 1200 times 500 plus 450 times 300. This will be 735,000 Newton millimeter. Okay, now the equation can be extended. You just substitute the Tx by this number, 735,000 times 37.5 over J is here. Right, it's a 1.834 million. And this will be 15.03 MPa. So what is the direction? Okay, we need to draw this cross section again. Let's draw it here. This is the cross section. And your point H is here. And this is the Y direction. And this is your Z direction. Okay. So the X direction is here, right, pointing out. Right, use your right hand rule. When you have a positive, torque, tau x, Tx, right? So this cross section will be rotated in this direction, right? So this is the tau x, the Tx, right? So the shear at point H will be pointing left, right? This will be pointing left or in positive Z direction, right? So this is the direction. Since if we have more than one component, you need to consider their directions to determine how to add them together, right? If they have the same sign or not. Then we will examine the other two components. The first one, tau 2, due to Vy. So this will be just Vy times Q at point H, Y, okay, over IT. Now here, what is the QHY? Okay. When you have a Vx along positive Y direction, if you use this equation to determine the shear stress, you cut it, you will cut it from here. You will cut it from here. Then what is the area? You will get area that is 0, right? So the Q will be 0, right? So here, this thing equals 0, right? So as a result, the overall thing will be 0, right? Because of this analysis, you just analyze that the tau 2 will be 0, right? Then how about the third component? Tau 3 due to Vz. Vz times QHZ over IT. Right, in this case, where you're cutting it, when you using the Vz as a shear along the positive Z direction, you just cut it from here, and you get this area. Okay, we had this equation to determine the Q here. It's just the Q max. Right, this will be the Q max for a circular cross section. Right, you just use the Q max equals Q max. Okay, so we can substitute numbers in this equation. The Vz, what is the Vz? Vz is 450. Okay, so here is a 450 times Q max, determined here. Right, it's 17160 over I is 917,000 times the thickness. Thickness is 7.5, but okay, go back to the slides in chapter 7. Okay, here you need a 2, right? For this case, for such a case, you need a 2 here. Okay, we need 2 times of the thickness as the thickness in this equation, in this VQ over IT. Okay, go back to the slides of chapter 7 to get more details there. Okay, so this is important to keep this times 2 in mind. Okay, then here you will get a result that is 0.56 MPa. So what is the direction? What is direction? Since the V is along positive z direction, so this thing will be along positive z direction too. Okay, so then we can determine the overall tau value for point H by adding the 3 together. Since they have the same sign, just add them together by 15.03 plus 0 plus 0.56. You have 15.68 MPa. Okay, so this is the result of the overall shear stress. So far, we have determined the normal and shear stresses at point H. Okay, so we have explained the whole detail here, how to determine the shear stress at a point by considering torque and the shear forces. Right. So if you're interested, you're highly suggested to go back to the previous example to repeat this process to find out the shear stress at that point K, okay, by yourself. Okay, do this exercise.